Hello, my name is Jacob Butera. I am a senior in aerospace engineering at Mississippi State University. Today I am presenting my senior seminar, Flight Performance of a Novel Fixed-Wing UAS. The purpose of this project is to analytically determine the flight performance of an unmanned aerial system developed by Exhibitor UAS student design team. As a secondary objective, the model was used to determine if the aircraft could complete its intended mission. A rendering of the system, dubbed ZOC 7B, can be seen in the bottom left corner. All dimensions of Figure 1 are given in inches. The aircraft has a wingspan of 8.5 feet and a length from nose to tail of approximately 6 feet. The aircraft stands just over 2 feet in height from the ground and has a maximum takeoff weight of 45 pounds. At full throttle, the aircraft produces 15.5 pounds of thrust at 7,500 revolutions per minute. This aircraft is intended to take off, climb to 500 feet, and cruise an approximately 6-mile waypoint course. After which, it's intended to descend and land fully autonomously. To simulate this mission, a MATLAB script was created, and the aircraft geometry was input into the script. The next step was to determine the lift and drag via component buildup method. This allowed me to compute the lift generated by all aerodynamic surfaces, including the wings and tail, and the drag due to each component of the airframe, such as the fuselage and landing gear. Those values could be summed to determine a drag coefficient for the aircraft. The next step was to determine the thrust as a function of forward airspeed, the results of which can be seen in Figure 2. Also in Figure 2, I've included the stall velocity, cruise velocity, and max velocity, so that the thrust available at each of those points can be seen. With all of this complete, I was ready to directly compute the performance parameters. Table 1 shows all of the performance parameters broken down by their flight regimes. First is takeoff. The aircraft is computed to have a ground run of 161 feet. During climb, the aircraft is expected to have a rate of climb of 915 feet per minute, a time to climb of 26 seconds, and a ground distance covered during the climb of 648 feet. The cruise range, assuming a 70% throttle setting, is predicted to be 30.5 miles. The turning performance was computed assuming a 45-degree bank angle. The rate of turn is computed to be 27.3 degrees per second, and the minimum turn radius was expected to be 141 feet. The glide performance was computed in the event of an engine-out scenario. The maximum glide range is 0.86 miles, and the time to glide is 1.25 minutes. Both of these values are computed assuming the aircraft begins its glide at its 500-foot cruise altitude. It is worth noting that both of these parameters are mutually exclusive. The aircraft, when it begins its glide, can either glide for maximum range or maximum endurance, but not both. Lastly is the landing run, in which the ground run was computed to be 113 feet. In conclusion, this aircraft has a 30-mile predicted range, which is much greater than the 6 miles required. During its 6-mile waypoint course, the aircraft will be expected to change its heading via banked turns. This aircraft is expected to be sufficiently maneuverable to accomplish this entire waypoint course. Lastly, the takeoff and landing runs can be accommodated at any airfield, as both ground runs are less than 200 feet. Therefore, according to this model, it can be concluded that the aircraft can complete its intended mission. Further work on this topic should include a flight test campaign consisting of a minimum of 3 flights for model validation. Luckily, this aircraft does possess a full avionics suite, which is more than capable of collecting all data necessary for a flight test. Thank you for listening to my presentation, and I will be happy to answer any questions.